Okay. Let's take a look at another game. We will not be able to finish this topic, but I'd still like to give you a taste, an idea of what's coming so that in the future, if you're interested, you can learn on your own. There's quite a number of topics that we were not able to cover. I teach slowly for somehow much slower than my friends, my colleagues. But I believe that you have now the necessary background to add on top of what we have done. Okay? So, before the example, we talked about pure strategies and extensive form games. How would you extend the idea of randomizing in extensive form games? Sorry? Probabilities over what? So that's one thing, but well, that we can add, but that's not a big problem, okay? If we understand how we'll deal with the randomization of agents, okay? Because if we understand that, putting chance into the game would be easy, because chance is a player who plays a random, takes a random action. The only thing is, he or she has already decided on what to do. So there's no optimization problem that we have to solve for chance, okay? So, how would you introduce randomization on extensive form games? If you were to say that we didn't have time to cover this topic, you're left on your own. You should be able to. We can't teach everything that you're going to face in life. Some of the things you have to learn how to construct them yourself. What would you do? Be creative. I don't know. Just drawing a picture just to give you some idea. Yes, sir.
I will give a probability that agent 1 will play L.
So talking about this, what about these? You would do. So how would you model? Different. So we transform this to strategic form game. So you have S1, S2, or other things, and exactly. You see, that's one trick that we keep doing in mathematics and economics. When we face with a new problem, we translate it into something that we know. We translate it into a problem that we know how to deal with, analyze that in that framework. So as your friend said, well, these games we can transfer into strategic form games. And we know how randomization works in strategic form games, okay? It was what we called a mixed strategy. It was a probability distribution over the agent's strategy sets, okay? So a mixed strategy in an extensive form game is a probability distribution over the strategy sets, okay? So far, so good? Okay? But is that the only reasonable way to handle this thing? For example, your friend had a little different idea. He said, when I come here, I'll choose L with some probability, P with, so I'll flip a coin. If it's head, I'll choose L. If it's tail, I'll choose R. And then if I come to this information set, I'll roll a die. Okay. If the number on the top is less than or equal to 2, I'll choose L. Otherwise, I'll choose R. Yep. Probabilities over?
Like he believes. He's more concerned
Okay.
about probabilities the player to set to his
Okay. So beliefs are also important. We're going to come to that. But right now, I would like to see, just like in strategic form games, we introduced randomization, which was a probability measure of strategies. Okay. It was about the strategy. It was about an agent randomizing over its own strategies. So for now, I would like to concentrate on that, but we're going to get to that too. We're going to get into beliefs too. Okay? So, as we said, as your friend said, one idea is a probability measure over the strategy set of the agent. Okay? So a mixed strategy of agent 1. In this extensive form game, a mixed strategy of agent 1 is a probability measure over S1, a probability measure over complete plans of action of player 1. Alternatively, what we can think about, that's one way. So before the game starts, okay, actually for here, let's write this. His strategy set is L, 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 R, R, L, R, R. Okay? So before the game starts, he decides on a probability measure over this set. I don't know, 1 over 3. Well, I'll keep it like that, otherwise I'll make some arithmetic mistake. Okay? So it says, I'll choose this strategy with probability 1 over 3, this one with probability 1 over 3, this one with probability 0, with this one with probability 1 over 3. Okay? So he puts 3 balls in a bag. On one of them it says LR, the other one says LL, LR, RR. So he picks one of the balls at random, looks at it, and plays what it's written on the ball. So once he decides on the random device, what he's going to do throughout the game is already decided. Okay, once the random device is chosen. Okay? Alternatively, what he could do is, well, at this node, when he has to take an action, he randomizes over L and R. He flips a coin, head, choose L, tail, choose R. Okay? And then, if he chose R and player 2 chose B, he's in this information set. Well, now I have to make a decision again. Again, he says, I'll randomize over the actions that is available to me. That is, I'll randomize over L and R. I'll roll a die. If it's less, the number that shows up on the top is less than or equal to 2, I'll choose L. Otherwise, I'll choose R. Okay? So what kind of an animal? The first animal we know already from strategic form games. It's a probability. So that's mu1. The second animal, the one that I just described, we give it a different name. We call it a behavioral. Of player I in the game gamma, in the extensive form gamma, is, well, what is it? Well, it's a list of probability measures. It's a probability measure over capital N and R. and another probability measure over small l and small r. That is, for each information set, we have a probability measure. Is a tuple of, I'll write them in a minute, sigma I. We used mu for mixed strategy, sigma. So actually, normally I would like to use B. I would like to use beta for behavioral strategy, but we keep the letter B. We reserve the letter B for what your friend mentioned, beliefs. That's why I'm going to use sigma of strategy. Okay, sigma capital I. Okay, where capital I is an information set of agent I. Okay, is a tuple. So what kind of animals is these? These are probability measures, tuple of. And what do I want? I want the probability measure used, that is the random device used to choose between L and R, to be stochastically independent, that is independent in the probability sense, of the random device used to choose between capital L and capital R. So it's a tuple of independent probability measures where for any capital I, for any information set of agent I, sigma I capital I is a probability measure over the actions available at the information set capital I. Okay, so this is a mixed strategy, a behavioral strategy of player one. Okay, consists of, there is two information sets, so I have to talk about sigma 1 I1 and sigma 2 I2, where sigma 1 is a probability measure of over the set LR. So this is sigma 1 I1 R L. With what probability will L be played? Sigma 1 capital I R. With what probability R is going to be played? So that's our first probability measure. The second one, this one, is going to be sigma 2 I2 L. That's an L. Sigma 2 I2 R. Okay? That's it. Okay? Where these two numbers should add up to 1, these two numbers should add up to 1. So an example for this could be, let me write it over here, 1 over 2, 1 over 2, 1 over, I don't know, 3, 2 over 3. Okay? So at this information set, capital L is selected with probability 1 over 2. Capital R is selected with probability 1 over 2. At this information set, small l is selected with probability 1 over 3. Small r is selected with probability 2 over 3. Yep? Sigma 1? I'm sorry. I didn't write that down, but I used bad notation. This is what I was thinking, but let's use this. I1 prime, I1 double prime. So let me fix this. I'm sorry about that. I1 prime, I1 double prime. Sorry?
Subscript of sigma.
Subscript of? Oh, these are, yeah, thank you. But this is also bad notation. We usually use subscript to denote the agent. So Yeah, thank you. Those should be 2, and let me make these 1. That's... Okay. Anyhow, you get the message. Okay, so far so good? So far, so good? So, the question is, we have 2 ways to introduce randomization into extensive form games. Which one should we use? Sorry?
Can't we turn this one into the other one?
Can't we turn the behavioral strategy into, so what do you mean by turn it?
I mean, the probability we will assign to one complete set of extras, LL, we can derive it from this by multiplying the one for large L and small L.
You had a question or comment?
We can transform this form to the other form that we know, but they are not equivalent. They are not the same because the old form, for example, you choose 1/3, 1/3, 0, 1/3. You cannot transform to this one.
You cannot?
Transform it to this one.
Okay, again, what do we mean by transform? That we have to agree on. So we're transforming something, but what are we transforming? And what is the aim of the transformation?
The probability measures.
Okay, so under what case will they be equivalent? There are 2 different kinds of animals. So under what condition will we call them equivalent?
Transform is not maybe a good word, but I mean the behavioral strategy contains at least as much information as the other one, and more.
Uh-huh.
We should use
That one? Okay. Well, question.
They are the same when the probability of each of them being played, given that the first one would prior action was taken, is equals to the probability of sigma 1 of the deformation condition.
Let's see. So first of all, there are 2 different kinds of animals. So if we're going to say equivalent, transform one in the other one, transform one form to another, okay, we should have some aim at it. We should have some maybe equivalence relation between. And the reasonable equivalence relation could be a probability distribution over the outcomes. Okay? So if, for example, a mixed strategy profile and a behavioral strategy profile have the same probability distribution over the outcomes, it means that agents will have the same expected utility, expected payoff, under the behavioral strategy and the mixed strategy. Okay? So equivalence, we will understand, from equivalence what we will understand is, if they have the same probability distribution over the outcomes, the terminal histories. Okay? So then the question becomes, given any behavioral strategy profile, can we construct a mixed strategy profile which will induce the same probability distribution over the terminal histories and vice versa? If we can go both ways, it means that they're actually equivalent. So we can use whichever one we want to. Okay? If they are not, then we have to be careful. Okay? Well, actually, let me write this a bit cleaner. Let me rewrite that. So for now, let's keep things simple. Let's take pure strategies in any sense for player 2. So if he comes to this information set, he's going to play B. If he comes to this information set, he's going to play A. Let's take the behavioral strategy. Let's start with that of player 1. So we said 1 over 2, 1 over 2. That's how I'm going to. So with at this information set, he'll choose L with probability 1 over 2, R with probability 1 over 2. Sometimes people put boxes around them because these could also be numbers to discriminate between an action and a probability. And when he's here, he chooses L with probability 1 over 3 and R with probability 2 over 3. Of course, the same thing. That's 1 over 3, 2 over 3. LR. So, what is the probability induced, given this behavioral strategy profile, what is the probability measure induced on the terminal histories? So this terminal history will be realized with probability 0. This one with probability, I should use it, 0. 1 over 2. This one with 1 over 2 times 1 over 3. This one with 1 over 2 times 1 over 3. This one with this one with 0, given that, and this one with 0. And then when we add them up, oh, this should be, I'm sorry. Okay, just when I was adding, so you should always check, it's most of the time it's easy to see your mistakes. I was adding them up. I just realized that they don't add up to 1 because I made a mistake here. Rather than 2 over 3, I wrote 1 over 3. Okay, so is there a mixed strategy of player 1 and 2 which induces the same probability measure over terminal histories? That is, we're trying to assign so this is the strategy set of player 1. So we're trying to assign a probability measure over this set, that is, assign numbers to these strategies that would induce the same sorry?
Like the independent probabilities, you can multiply them. For example, LL will be 1 over 2 times 1 over 3.
LL will be 1 over 2 times 1 over 3. Everybody agree with that? Everybody agree with that? Well, first of all, there's nothing to do with player 2, so we'll keep that away. So if player 1 decides to use a probability measure for which this is the case, with what probability will this, or, well, I have to write that too. So let's finish the whole thing. What about this? 1 over 2 times 2 over 3. Sorry? 1 over 2 times 1 over 3. And then 1 over 2 times 1 over, I'm sorry, again, I made the 2 over 3. Does that induce the same probability distribution over the outcomes? Well, let's check. So which case leads to this outcome? That outcome be realized when when either one of these strategies is used by player 1, given that player 2 is using this strategy. So with what probability will we have that? It will be 2 over 3 times 1 over 3 plus 1 over 2 times 2 over 3, which is 1 over 2. Pass the test. What about this? That will be realized with when player 1 uses this strategy and the strategy at which he plays R at the initial node and L at this node. That is, where's that? RL. It's this, which is exactly that number. And the same thing here. Okay? So, what did we do? For that behavioral strategy, we found a mixed strategy, which is outcome equivalent. They have the same probability measure over the terminal histories. So we were able to, yes, sir.
Like when I come to the like this node,
Come again, I couldn't hear that.
when I come to the node that I play small L,
This one or this one? Oh, player 1 comes here.
shouldn't I know that agents played this probability by that one, so should it be conditional?
For what? I'm not sure I understood.
Like when play agent 2 played A,
Uh-huh.
in probability maybe.
Okay.
Shouldn't this form my new universal?
Okay. Now, what you're coming to here is, again, probably about beliefs, which we'll get into. But first, I would like to deal with randomization of the agents over their own actions. Okay? And we will talk about, I hope we will talk about beliefs. But so let me go a bit fast. Is that, I'm not sure whether that's what your question was. But we'll get, so let me speed up a bit because we're not going to have any time to do it. So actually, what we have is, given any behavioral strategy, any extensive form game, given any extensive form game, any behavioral strategy profile of the agents in that extensive form game, there is a mixed strategy profile which induces the same probability measure over terminal histories. Now, the other way around is not always true. But it is true for most interesting cases. What is not, it's not true for games of the following form. So let me give you an example of a game, a simple one. Player 1 chooses L or R. Then player 2 chooses between A and B. And then if he chooses B, the game ends. If he chooses A, it's again player 1's turn to move. Can choose between L and R. The thing is, these two nodes are in the same information set. So how can that happen? Well, player 1 forgets what he has done, just like I forgot that I have given the attendance sheet, which I just remembered. I didn't give the attendance sheet. Okay. Right? Just like I forgot that I give the attendance sheet in the first lecture, he forgot whether he played L or R. Okay? So the reason that I said that, for most games, the two will be equivalent. The equivalence might break in games. Well, actually, for this game, it breaks down. So if you have a game in which some of the players forgets what they have done in the past, then the equivalence breaks down. Okay? But if this is not the case, that is, if agents remember their own actions, they don't have to see the actions of other players. But they should not forget what they have done. If that is the case, then there is the equivalence. Okay? For every behavioral strategy, there is a mixed strategy, and for every behavioral strategy profile, there is a mixed strategy profile. For every mixed strategy profile, there is a behavioral strategy profile that yields the same probability distribution over the terminal histories. Okay? Unfortunately, I don't have the time to give you the formal definitions because we have to write some induced probabilities and all that stuff, but the idea is that. So games in which agents do not forget what they have done in the past are called perfect recall games. They can remember what they have done in the past. So this is not a game of perfect recall because player one forgot that he played L or R. Okay? So in such games, actually I do have an example for that. So here S1 is L, 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 R, R, L, R, R. S2 is just AB. Take the mixed strategy profile. Yeah. 1/2, 0, 0, 1/2, and 1, 0. Okay? There is no behavioral strategy. There is no behavioral strategy which is outcome equivalent to this. So that's mu1. That's mu2. There is no behavioral strategy profile which is outcome equivalent to this mixed strategy profile. Okay? And it's easy to show, actually, given that we will not have much more time to do anything new. So if that's what is used, what will happen? This outcome will be realized with probability 1/2. This one with probability 0. This one with probability 1/2. This one with 0. This one with 0. So those are probabilities. Right? So let's say that there is a behavioral strategy which induces the same probability measure. That is, there is sigma 1 and sigma 2, which induces the same probability measure. Then what does that say? Sigma 1 of, so I'll call this I11, and I'll call this I12. Sigma 1 of I11 at L times sigma 1 of I12 times at L. So this times this should give us 1/2, right? So how do we come here? Player 1 plays L here and plays small l here. Okay? Also, what do we have? Sigma 1 of I1 R times sigma 2 of, well, I'll just call I2 because he has only one information set, of A times sigma 1 of I, that's 1, 1, I1, 2 at, by the way, I did make a mistake here, right? This is 0, and this is 1/2. He plays R with probability 0. Okay? Okay? So far, so good? Well, what does that imply? It implies that this number is positive. It implies that this number is positive. Otherwise, the product will not be equal to 1. Which implies that sigma 1 of I1, 1L times sigma 1 of I1 to R is positive. But what is that? That's the probability that of this terminal history, this outcome being realized when this behavioral strategy is used. But it should have been 0. It's not. Okay? So in such games, behavioral strategies and mixed strategies are not equivalent in the sense that they do not induce the same probability measures over terminal histories. Okay? Hence, most of the time, most of the games that we play with, that we study, are games with perfect recall. Such situations do not happen. And in such games, we don't have the time to prove it, but in such games, behavioral strategies are equivalent to mixed strategies in the sense that I have already talked about, which means that you can use either one of them. Okay? So far, so good? So far, so good? So, if your game is perfect recall, use whichever one you like. Usually, we prefer behavioral strategies because it's intuitively more appealing. Okay? Mathematically, it's a bit more complicated object. It's a list of probability measures. Okay, so it's a bit more complicated, but still, it's more intuitive. Now, for the last couple of minutes, let's do a very simple example. Player 1 starts. He has 3 actions to choose from. If he chooses R, the game ends, and the associated payoffs are 1, 4. If he chooses L or M, then it's player 2's turn to take an action, but player 2 is not informed about this. So he has to choose between small l, small r, small l, small r, and the payoffs are 3, 3, 1, 0, 2, 1, 0, 2. Okay. So, what do? We modeled it. The first thing we look for is Nash solutions, or the next step would be subgame perfect Nash solutions. We know that Nash solutions could involve some unreasonable strategy profiles. So for extensive form games, sometimes we prefer to look at subgame perfect Nash solutions. How many subgames does this game have? Only one, right? So actually, the subgame perfect Nash solutions and the Nash solutions of this game are the same, no difference. So how do I find them? Well, I'll write the strategic form equivalent of this. So what will it be? Mark the best responses. That's a best response of player 1. These are best responses. So L and R are best response to small r. Capital L is a best response to small l. And for player 2, small l is a best response to capital, small r to capital M, both of them. So the set of Nash solutions of this game, which is the same as the subgame perfect Nash solutions of this game, are L, 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 that's one profile, and R, R. And then, of course, we can look at mixed strategies. And you should look at it. I'm not going to, given the time restrictions, I'm not going to look at the mixed strategy Nash solutions of this game. But let's look at this game. So this, player 1 choosing the action R at this history, and player 2 choosing the action R at this history, at this information set, is a Nash solution of it. And it's also a subgame because this game doesn't have any subgame other than itself. Okay? But now, put yourself in the shoes of player 2. Player 2 does not know whether player 1 has played L or M. But if player 2 knows the strategies of player, knows the preferences of player 1, and also knows that player 1 is rational, what would player 2 think about the action of player 1? He must have played L, right? So you see, if he plays L, if he thinks that I'm going to play small l at that information set, if he plays capital L, his payoff is going to be either 3 or 2. If he plays capital M, his payoff is going to be either 1 or 0. So what he will obtain by L, whether if he knows that I'm going to play L, what did I say? Yeah, if he plays L, my payoff is, I'm sorry, I'm rushing to finish it, but if he knows that I'm going to play L, if he thinks that I'm going to play L, if he plays capital L, his payoff is going to be 3. If he plays capital M, his payoff is going to be 2. 3 is bigger than 2. If he believes that I'm going to play R, if he plays capital L, his payoff is going to be 1. If he plays capital M, his payoff is going to be 0. 1 is bigger than 0. L is better than M. So I would expect that he would play L. So if I'm player 2 and if it's my turn to take an action, I would believe that. I do not know it because I don't see it, but I would believe that player 1 played L with probability 1 and M with probability 0. Okay? So probabilities in many fields, in economics especially, we use to represent beliefs. Okay? The higher the probability, the stronger we believe that that event will occur, not has, will occur. Okay? So, okay? But then, if I believe that, if I'm at that information set, I believe that he played L with probability 1, then what is the best thing for me to do if I'm player 2? To play L, not R. So this Nash solution is not a reasonable Nash solution. Okay? Okay? Why? Because the belief which is consistent with the action of player 1 is not, well, my action at this strategy profile, my action at this information set is not in accord with my belief, which is consistent with the action of player 1. Okay? So we rule that out. Hence, this is reasonable, but there might be other. Okay? So what we do is, the next thing again, so we run into a problem. As game theorists, what we do, we invent a new solution concept. Okay? People complain that in game theory there are too many solution concepts. Okay? Usually people are used to the fact that every problem has a solution and the solution is unique. Well, life is not that simple. Many problems don't have solutions. Some of them have a single solution. Some of them have more than one solution. That's why in game theory, we have many solution concepts. Each and every one of them has its pros and cons. The concept that we don't have the time, I have to stop now, but the concept, if we had time, that I would build on this is called weak sequential solution concept. If you're interested, you can take a look into it. But then what we mean by a solution is a pair which consists of a belief over information sets together with a behavioral strategy, okay, of each agent. So for each agent, we define a belief over information sets for each information set and a behavioral strategy. And if that list satisfies certain conditions, which we briefly explained here, we call it a weak sequential equilibrium. But unfortunately, we don't have the time. So I'm sorry that we couldn't cover everything that I hoped we would be able to do it. But I hope that you learned something out of this course and also enjoyed it while you were learning it. It was fun for me. I hope it was for you too. As I said,